can begin.
Okay. I work in the field of 2D materials and transition metal digital cogonites for 36 years now. And day in, day out, probably I'm the oldest person practicing 2D materials for such a long time. And looking back at what happened during this time, I have acquired some perspective to the field of 2D materials, which is so popular nowadays. And I started my talk today by presenting a perspective of the field that started actually almost 100 years ago. And I presented a few papers which go back to 1921, 1922, 1923. And this is actually the first scientific work on 2D materials. And that time, of course, people had very primitive tools to investigate 2D materials. But they already acquired some knowledge that we are benefiting from now, from their knowledge that they have acquired. And with time, electron microscopy started to enter into the field because the first thing that people could measure was basically very rudimentary techniques like X-ray, some spectroscopy, and their tools were very primitive in a way. But also the models and the understanding was so in a preliminary way, or if there was so little knowledge that things were understood on a very, very rudimentary basis. So with time, electron microscopy, spectroscopy, and all other techniques that we are nowadays using started to get in. Cryo and measuring things at low temperatures, and the physical understanding of what these materials became relevant. In particular, people started to understand that these materials are very anisotropic, and they have many of their properties, or actually almost all their properties, are influenced by the great anisotropy of the material. And at that early time already, I mean, before Second World War, the knowledge of material science was very rudimentary. So methods to synthesize these materials were very primitive. And most people actually worked on materials that are available in nature, like alumosilicates, layered alumisilicates, and molybdenite, which was available, and some other double hydroxides, etc. After Second World War, especially in the 60s, scientific concepts started to develop, and knowledge has become about these materials exploded almost exponentially. And at that time already, some ideas about what happens when you cleave these materials to very small sizes started to evolve. And with that, people have already in the 60s, early 60s, and beginning or late 60s, people started to understand the concept of quantum size confinement, but there was still nothing relevant to nanosciences at that time. It took another 20, 30 years to the 90s, actually. I got interested in this material for solar energy conversion, following the works of Helmut Tribuch and others. And I got interested in using these materials for solar energy conversion. And at a certain point, I realized that these materials have very unique nanostructure, nano behavior. And as soon as or after carbon nanotubes were discovered, I realized that you can prepare nanotubes and fullerene-like structures from molybdenum disulfide, tungsten disulfide. They all suffer from the same instability, namely the edge effects that lead to their, when you bring them to the nano size, they have so many atoms as rim atoms which suffer from dangling modes that they, upon heating and upon proper conditions, they fold and make nanotubes, fullerene-like structures, and I propose this as a conceptual development for the 2D materials. And this has evolved over the years. We have synthesized many tubular structures and fullerene-like structures using different chemical techniques. So we developed a whole toolbox of chemical methods to synthesize these nanostructures. And working together with theorists, we have developed, or they have developed together with us, alone or with us, different methodologies to understand the physical behavior of this material, and eventually some interesting applications. For example, collaborating with my colleague Professor Lev Rappaport, I developed the first lubricant based on molybdenum disulfide and nanotubular or fullerene-like structures, and that has evolved over the years to an industrial undertaking. There's quite a number of companies now that are involved in manufacturing and commercialization of this product. So actually, I didn't have much time, but I showed that this application by itself is a huge field of application. And then just mentioning that we can use these materials for as fillers to composite, polymer composite, in order to enhance the properties of polymer composites, the mechanical, the thermal stability, even the conductivity, and some other properties. And that is actually developing now or into technologies that can be used for a variety of applications, which I didn't have time to elaborate. And I think that now that we have gained understanding that we can now control layers of these 2D materials, not only on the macroscopic scale, but on the nanoscopic phase, allows us to expand into different properties and different future applications which have never been thought of before.
Thank you very much. Thank you.
How long did it take?
That is 8 minutes 40 seconds.